my name's Simon. I'm going to be talking about some stuff I worked on a few years back. So hello. I currently work for a company called Cloudant. We're a database as a service company. This is the first talk I've given using the new version of Keynote. So if it goes dreadfully wrong, blame Apple. But before I worked at Cloudant, I worked at Bristol University in the physics department on one of the LHC experiments. This is CMS. There's a person there to give you an idea of scale. And I ran the data and workflow management group for that experiment. It's about 4,000 people spread over 100 and something institutes. To prove I'm a physicist, here's a plot. So places I've worked in the past. I sort of started working at Cloudant in March last year and was at Bristol since 2002. A further plot to prove that I'm a physicist. These are languages that I've written over the last kind of 10 years or so. You'll notice that I don't do much, or haven't done much Java. There was a brief dark period in 2005 when I wrote loads. So yeah, I feel a bit in the wrong audience maybe. But yeah, this is also completely made up while I was watching TV last night. So that's good. Let me just tweak this a bit. There we go. Okay, cool. So again, another sort of demonstration that I'm a physicist. Here's a complicated formula. It's not rigorously derived. I have had someone from MIT look it over. And of course, everyone will understand that G is fixed, and these C sub S and C sub C's are fixed, and Cn is usually fixed and stuff. In case there's one or two of you that don't understand this formula, don't know already, basically science is equivalent to the grant income that the person has times their effectiveness, and then divided by the cost of buying storage and compute, paying for the network over time, and the cost of the people that do the science, right? Things like storage and compute are basically one-time fixed costs. So I buy a cluster of 100 nodes or whatever, and that costs X, and I know that that's there. There's maybe tranches of hardware that I buy every year or 3 years or whatever. Variations in network cost I can amortize with some fairly careful planning. The thing that sort of starts coming out is that people are the important precious commodity kind of thing, and that's where you kind of want to maximize their output. Another way of looking at the equation is that people problems are the hard ones, and technical stuff are things that you can actually solve easier than sort of social or political ones. And we'll come back to that further down the talk. Before I kind of go into kind of the nitty-gritty lessons learned sort of stuff, I thought it'd be useful to kind of go through the life cycle of data taken at the LHC and kind of explain that to you guys. That's okay. So there's kind of 7 stages of data taken at one of these experiments. It's detected by the experiment itself, which is kind of obvious. There's some online filtering, which is both done in custom FPGA hardware and kind of a dedicated compute farm. The data is then transferred to the CERN. So CERN's in Geneva, obviously, on the French border. Data gets transferred to the main campus. It's archived to tape, because physicists love tape robots, especially if they get into a fight with each other. That's a good one. And then reconstructed, and we'll talk about that in a sec. It then gets transferred to tier 1 sites. These are kind of like large national labs, like Rutherford Appleton Laboratory in the UK, Fermilab in the US, for instance. It gets archived again on tape in case one of the robots at CERN becomes sentient and deletes all the data or something. Reconstructed again with sort of updated calibrations or whatever, and skimmed, which is kind of summarized and sort of extracting out kind of some high-level stuff. Then gets transferred down to tier 2 sites. These are universities in general. Sometimes they're big national labs that are kind of affiliated to the experiment but not on the experiment. And again, there's sort of further reconstruction, skimming, filtering, analysis going on there. Usually the result of that is kind of some locally analyzable file. People put it onto their laptops so they can work on planes or whatever. And then eventually it gets turned into a plot in a paper. So how do you detect something by an experiment? First of all, you dig a big tunnel. The CERN ring is 27 kilometers long. It's the same size as the circle line. except there's no trains, some bikes. That's about it. You then chain up a series of these kind of atom smashes. So the LHC is built in the tunnel of the previous experiment called LEP, but it's also powered by previous generations of accelerator, and they kind of all build up into this kind of one great big ring. It's the whacking great one at the top. You then put sensitive cameras in awkward places. It's not endoscopy, but it's similar. The fun thing with CMS is it's 100 meters underground, because that makes sense. And the interaction point, so on the previous slide, where you put these experiments, these yellow blobs, they're actually fairly precise. Like you can't kind of just whack an experiment anywhere on that ring. It's got to be where the beams are going to cross over. So CMS is actually in France, not in Geneva. And amusingly, it's, like I say, 100 meters underground. They didn't realize when they were digging the tunnel to put it underground that there was an underground river, right? So they're digging down. It's like, oh, this is quite wet. What do we do about this? And the answer, of course, is that you freeze the river with liquid nitrogen, dig through it, and then put guttering in. That actually is what we did. And the best bit of that story is that this happened in summer time. They froze this river, and it made all the roads slippery. And this guy crashed his car, right? Does his insurance claim. What happened? Oh, I skidded off on some ice. And the insurance company's like, yeah, pull the other one. So the DG of CERN had to write a letter saying, no, I assure you, he actually, we did freeze some things because we're crazy physicists. We then record these events. So this is a sort of simulation of, oh no, this is real first data. So you record these kind of collisions. Sort of standard running, the event sizes are about 1 megabyte per event. We just take billions and billions of them. We also do heavy ion running, and that's where you crash lead together. And those events are kind of like 10 times the size. So you're looking at kind of 10, 20 mega an event, which causes interesting problems for the processing. You then stick all that data into kind of these high-end machines. This is a really fun website, actually. This is one of the first computers at Rutherford Appleton Labs for, I think it was the first tape archive at Rutherford Appleton Labs in the 1970s, late 70s, I think. But if you go to chilterncomputing.org.uk, you can actually see photos of the kit they bought, and also see the kind of financial reports on what they bought for how much money, and it's kind of impressive that like 1 kilobyte of compute costs £10,000 or something. It's kind of amusing. It's a good site to have play around. And we basically use any and all technology in the computing system. So databases, we have a whacking great Oracle instance at CERN, runs a lot of our stuff. MySQL gets used, CouchDB, MongoDB, Postgres. They all get kind of used for different things. We're very agnostic to technology. It's kind of important to sort of pick up what's good. In terms of languages, we tend to write the sort of software that kind of glues everything together is generally Python and Perl. And I've got some scars with that one. And then the analysis software is all basically C++. And then we pick up kind of random tech. So there's a lot of homegrown storage systems, batch systems, all this sort of stuff. We also started using HDFS for storage system, which is quite nice. And there's been some recent work looking at using Hadoop for the processing stuff, but that's happened since I've left, unfortunately. When I suggested it, I got called a heretic, which was good fun. So step 2, online filtering in hardware and software. As I said earlier, we have a big digital camera, takes photos like that, which actually look like that because it's using an Instagram filter called overlaying events. The camera goes into lots of computers. This is called the HLT, high-level trigger. And that goes into lots of disk, which is called the storage manager. So we write out from the actual experiment, goes out about 200 gig a second. The actual data it takes is kind of more like petabytes per second, and it's the hardware triggers that can kind of filter out that stuff really, really quickly. The storage manager gets written to at about 2 gigasecond, and the storage manager basically works as a capacitor to sort of ease out the kind of the flow into the offline system. And then we kind of write out at 2 gigasecond to the rest of the world. So that's where the data gets transferred to CERN. the main campus archive reconstructed. The experiment takes about 10 petabytes of data a year, which is nice. That's stored in a file format called root. Root's a homegrown at CERN system that uses, well, it's an object database in a file. It's also a stats package, analysis package, a distributed file system, and other such crazy things. That's what happens if you let physicists write code. We tried to store files at sort of 2 gig a go, so it's kind of, the overhead of opening a file is quite large, especially if you're reading it from tape, so you want to kind of make that one read a big kind of processing thing. We take about 10 petabytes of data a year from the detector, but we also have to simulate comparable, if not larger amounts, to sort of compare what we think the physics is doing to what actually it is doing. So there's at least as much simulation. We also have lots of sort of duplication of that data, refined data, duplicates for making it easier to access that data, etc. Yeah, so because we've made a ton of duplication of the stuff, we want to sort of spread it around to these sites. So we want to get it out to the universities where people can do their kind of analysis. So that's where we do these kind of large transfers to tier 1 and tier 2 sites. One of the systems I worked on was this thing called FedEx, Physics Experimental Data Export. And so this thing's running, this is a plot for the last 18 months, I think. So it's basically running kind of petabyte plus a week transfer around the world, going to 100 odd different sites, which is kind of cool. It's equivalent to sending like a DVD of physics data to everyone in Bristol, which is where I live. No one in Bristol would want a DVD of physics data, but the guys at the universities do. Interesting thing here is that this is WAN traffic, so it's using sort of semi-public internet. Goes across the Atlantic. One of the reasons why we built this kind of very hierarchical and push out data to the edge of that system was that when the experiments were being designed, the expectation was that the transatlantic network wouldn't actually work, wouldn't be good enough to kind of stream data out to the guys in the US. And so there's this kind of idea of like, well, why don't we push as much of it to Fermilab, and then kind of from Fermilab that would act as kind of a local hub for American analysts to go. And there's a nice plot of kind of stuff that I think it was a guy from Stanford, Slack, had bought, and it's kind of, you know, CPU was following Moore's law, and disk was following Moore's law, and IOPS were following Moore's law, and network kind of just kind of steps. And so they were planning this kind of, I guess, late 90s. And then things like Google and Facebook and Flickr and whatnot took off, and suddenly the transatlantic network's not a problem, and now it's kind of, the network's kind of one of the most reliable pieces of the computing infrastructure for these experiments, and they're now kind of looking at how to break that instead of breaking disks. Yeah, as I said earlier, all data gets written to tape at the tier 1 systems, sites, sorry. And that's in case, like I say, the CERN robot blew up, or CERN were hit by a meteorite or whatever. So why transfer so much data? Well, there's kind of this original kind of problem that they thought would be a transatlantic network. But it also can't really exist at a single site, right? The politics around these experiments is phenomenal. So having, you know, if the Italian group is the only one that gets the Higgs data set, then there'll be a riot, which is kind of fun. Also, things like power budget. You actually would have a very hard time building a large enough data center in the middle of Geneva to host and process it all. And then the last kind of reason is cost. So the cost of the LHC computing is kind of on a similar scale to the cost of the LHC itself. And so you have this thing of like, well, we're not going to be able to ask a research council for the same check again. They don't like that. Whereas if you say, oh, we're going to put loads of computers in universities, can you give the universities some money for those computers, then that seemed to work out quite well. So yeah, it's many sites, I think 110 or so. Hundreds of petabytes of storage distributed globally, tens of thousands of worker nodes. And the reason why you have to have so many worker nodes is because to process all the data taken in 1 year would take 64,000 years, which isn't great if you want to get a Nobel Prize, because you'd have to start doing it when modern humans reach Geneva from Africa, which is kind of, until we build time machines, it's problematic. And then the last sort of kind of life steps in the lifetime of data is making these kind of locally analyzable files and making up the paper. So each analysis is approximately unique. And again, there's 4,000 people or so kind of churning out stuff. There are hundreds of analyses going on at any one time. Query language is C++, quite often fairly ropey C++, more often than not Fortran written in C++, which is great. Runs on both distributed systems and local resources, so people will have access to this kind of large compute grid thing, but also access to local batch farms or a honking great beefy server to sort of do the processing. The analysis is basically a series of cut selections, so you're saying, I believe that my signal will be in this region of some axis, and background will be in that region, so if I exclude stuff in that region, I can amplify the signal over the background. And the data that's in the final plot is often substantially smaller than the original data set. So people will skim through these kind of tens of petabytes of data, but actually kind of end up processing stuff in sort of hundreds of megabytes kind of size. And part of that is this, this idea of kind of a workflow ladder. So the idea is that we have these kind of very large data sets where there's very complicated computations run on them, and they're all run on this large distributed compute system, and kind of done for the benefit of the whole collaboration. So I don't know, reprocessing with a new set of calibrations, you'd want to run for everybody, right? And so these kind of large data sets are usable by the majority of the collaboration and are done centrally. You then kind of go down and you kind of start seeing simpler computations, so less intensive compute runs, building up kind of shared data sets that are more targeted at initially physics groups and then specific analyses. And then you kind of come down to this kind of sort of semi-private and private data sets where they're much smaller, simple computations, stuff that you can run on laptops, and that's the stuff that ends up in the paper. The important thing is that people can sort of work and move through this ladder as they need to, right? So often people maybe start down here and build some simulation, toy Monte Carlo stuff, saying, I think this is what's going on. Is it worth me investigating further? And then they'll go, yes, it is, and they'll get approval to do a big run on everything, and then gradually work back down again. So yeah, the other side is that there's simulation data, and it has a very sort of similar life cycle, simulated by the experiments at tier 0, tier 1, tier 2 sites, transferred around, archived, et cetera, made into local files, and turned into plots in paper. Part of the thing there is that the reason why Monte Carlo is so important is that you don't necessarily know, or the way you can say that your physics theory is correct is by saying, here's a simulation of my physics theory, does it look like the real data, right? The sort of rare events, the rare sort of new physics stuff, so say you're looking for supersymmetry, you would maybe have, like, after all the selections, you'd maybe have 10 or 100 events from an original sample of billions, right? So a lot of stuff gets kind of cut out. And yeah, this sort of rarer, or the new physics stuff, is kind of masked by what were interesting discoveries tens of years ago, and require kind of more statistics to be able to kind of push through and demonstrate that stuff. So most events kind of get cut out. So billions and billions of events, and you end up with kind of thousands or maybe a million. And it's kind of depressing, and you kind of end up in this kind of, when I wrote this talk, I was a bit jet lagged, and I was in a bad mood. And so you end up in this kind of Dawkins-esque kind of, most of us are going to die. And then I kind of cheered myself up by thinking, actually, it's more like Lemmings, and there are some levels in Lemmings where you can win with just one guy. So that's good. So that's how we take data, how we process it, how we move it around. And then I wanted to kind of talk about the adoption and use, and how this sort of, some of these ideas can kind of relate into use elsewhere, right? So as I said earlier, we have a slightly different sort of setup to most people. hundreds of sites, hundreds of terabytes of storage, tens of thousands of worker nodes, very global system. Again, can't be a single site because of politics and power and cost. It's connected through this thing called the grid, or Tron. And the grid's basically a set of middleware. A lot of it is written in Java, actually, that's essentially sitting on top of different schedulers. So you'll have a local batch system like LSF or PBS or Talk Maui, and there'll be a thing on top of that that knows how to communicate the state of that batch farm to sort of the global system, pull in work. Similarly, for the data transfer stuff, there's kind of again, another kind of queuing system that sort of says this site can accept X number of files per second, queue them up, keep them busy. And the sort of thing that was always and is always problematic has been the storage system. So things like HDFS are interesting because they're something that we didn't write ourselves. They're kind of demonstrated to work at kind of useful, comparable scales. And there's a kind of a much larger community around things like HDFS than something like Dcache, for instance, where it's kind of very niche and very targeted at the high energy physics communities. Right. So yeah, there was a nice thing, a tweet that went past a while back, where someone said, we have a big data problem. And this is that companies seem to think that by collecting data, throwing it into some Hadoop system or whatever, you can magically discover value in it after the fact, right? There's unicorns in that log data or whatever. The actual better phrasing of it is that we have a big data problem. People aren't very good at phrasing a question as an experiment, right? So people just collecting log data won't tell you that your users are getting bored with your traffic. You need to understand that the conditions and be able to kind of phrase, how do I make this, how do I make engagement on the site increase by 20% or whatever? It has to be phrased as an experiment so that you can go out, collect the right data, and kind of answer that question through a sort of more rigorous scientific kind of approach. And that's something that academic folk are quite good at. And it seems to be something that's kind of gradually percolating out into sort of more enterprisey kind of software stacks. One thing that we, as an organisation, started kind of focusing on was this kind of, do what you do best, outsource everything else. And we sort of were doing that internally. So we had a team of folk who were the guys that were building and understood how this distributed computing system worked. We spent a significant amount of time making sure that other folk didn't have to worry about it, right? You don't want to have 4,000 people explaining the sort of intricacies of the queuing system at a site. And this is kind of the essence of the cloudy kind of stuff. The assumption in sort of academic lands is that everyone can and will write the tooling they need, which isn't necessarily the best use of people's time. So we had this sort of team of people who are focused on delivering the software. We had a team of folk who was focused on delivering these kind of initial reconstructions and initial skims to avoid kind of duplicating the effort across groups of people. And that seemed to sort of work quite nicely. One of the things is interesting is that big data isn't particularly interesting anymore, at least to me. Doesn't mean it's easy, but you're now in a situation where you can kind of pick off-the-shelf commodity hardware, software, and not have to think about it. Whereas 10 years ago, building a terabyte server was like 3U boxes that were kind of large and expensive. Now it's kind of I've got a terabyte disk that's like that big on my desk. It's silly. So unless you're kind of at a scale similar to Google, and it is basically Google, you don't need to go and write your own system. That's kind of an interesting thing. One of the problems that you have there is that you have the Knights of Ni come along. So the not invented here is quite a difficult thing to get over, especially in sort of academic circles where the kind of the thrill of the chase, the building of the new thing is in and of itself useful and interesting. But yeah, nowadays you don't have to write your own system, so you can go and engage with existing projects. As the keynote was talking about, things like Apache kind of really emphasize that kind of community over code, aggregating efforts together. One of the things that we did, or tried to do, is kind of define and refine workflows. So as I said earlier, we had approximately 4,000 individual workflows, all roughly independent, but all running over that same data set. And so being able to kind of draw out common threads, this analysis needs to look at, I don't know, electrons and photons, and being able to kind of pull out those things nice and early so that reducing that sort of duplication of work was really useful. And being able to kind of establish that both the workflow through the system, but also the workflow or the process around refining it was very important. And being able to sort of prioritize and gauge that sort of hotness of the data. This is the interesting thing that everyone's going to want. Right, we're going to have to put it at as many sites as possible. Was pretty important. So one of our interesting sort of pieces of our situation was we had these very expert users. Everyone had a PhD or was on their way to getting one, and they really didn't give a toss about infrastructure. So if they could work out a way of using xargs and some hokey Perl script to completely denial of service attack every single piece of the system, they were happy because they got their jobs done better. They didn't notice that there were 4,000 angry people sitting next to them. And so they will work out ways of getting around any perceived unnecessary limitations. And it doesn't actually have to be an expert user necessarily that sidesteps the organisation. You get these things where, we had one university in particular quite liked kind of making a little shadow organisation that went off and built its own reconstruction software and stuff like that. And it's like, well, it's not actually very useful, and you're not going to get an approved paper out of that, so stop it. And so being able to kind of control and organise and focus these kind of large groups of people is something that's really difficult. And it happens in other places as well, right? This is who here doesn't know Francis Maude is, MP? So he basically got pissed off that he couldn't use his iPad at the Houses of Parliament because the Wi-Fi didn't work with an iPad, and so he set up his own Wi-Fi network, which obviously is then grossly insecure and stuff, and that's good. So you're always going to have these kind of disruptive users, and the trick is to sort of work out how to engage with them and kind of turn them into advocates, right? We found often that the guy that was most awkward and most difficult and most complaining, if you could sit down with him over a coffee and explain why the thing that he was butting his head against was there and that sort of stuff, if you could explain it to them such that they understood it and accepted it, they'd actually then become a really useful advocate, right? So that's a really nice thing, right? If you can say, the reason why we're doing this is to make everyone else happy, not just you. That's kind of much better than sort of the stick approach of we're going to rescind your access, right? Because that guy might be the guy who's going to get the Nobel Prize. And part of that is about making the right path, quotes, the easy one, right? Work out how to simplify things such that doing your own thing is more difficult than doing the sort of accepted kind of standard way. And that becomes kind of all around kind of building appropriate interfaces, listening to users, being kind of being on receive a lot more than perhaps you might do if you're just sitting down kind of coding all the time. Another way that you can sort of another way that you can kind of engage disruptive users is by taking the thing that they're interested in, which is the data set, right, and controlling how that gets accessed. So, and that's kind of more sticky approach as opposed to the carrot one. But that's kind of nice. You can say, we're going to make it very, very easy for you to transfer. In our case, we said, we're going to make it very, very easy for you to transfer tens of terabytes of data if you do it properly, right? If you want to do it by yourself, that's fine, go ahead, but it's going to cause you significant pain and injury. So that's kind of a tricky way to sort of push your agenda. To that point, we had a very, very, in CMS at least, we had a very, very open access kind of policy. Anyone in the organization could see and access any data. There was no kind of, you're in that group, you're not allowed to see it. There's a talk this afternoon by Bruno Saar about that, if you want to go and see it. So going back to this plot from earlier, all these data transfers, some of them were organized centrally. So there are some folk that were responsible for making sure that the Italians got their reconstructed data and the Americans got their reconstructed data and the English got their reconstructed data. But a lot of these transfers were triggered by normal physics users, and there's a web page you could go to and say, I want this data set at my site. Part of that was because we weren't paying network charges, So the interesting thing there is that we had a kind of an organizational human problem, and the way CMS solved it was a very human solution. We basically appointed for a given site, there was a person who had a data manager role, and they were able to, someone would go and fill in this form, they'd get sent an email saying, you know, Joe wants to transfer 10 terabytes of data to your site, is that okay? Yes, no, kind of thing. Interestingly, the experiment on the other side of the ring, Atlas, chose to go a much more programmatic route. And so they had these kind of defined policies that were really, really complicated, and I'm sure there was an ontology in there somewhere as well and stuff like that. And they just couldn't get that thing to work because it was such a complicated thing of like, you know, this guy is paid by this guy, so he should have some of the privileges from that guy, but not all of them, and da, da, da. Whereas our thing is like, email them if there's space, they'll say yes. Much simpler. So yeah, humans quite good at solving problems. Yeah, we had, we were in a situation where actually testing in production was in some ways the only solution, which isn't great. We obviously had substantial unit tests for all of our code, but if you're dealing with like a 100-site system where there's tens of thousands of nodes, there are edge cases and weirdnesses that you won't know about until you hit them. And so yeah, the actual issue is that it's not about the number of jobs necessarily, it's like this one's got a flaky network because it's connected to Bristol University or something like that. It also had a very strange organisation. Lots of chiefs, not many Indians kind of thing. You could trigger a sort of genuine international incident quite easily by saying the wrong thing to the wrong person. And there was an implicit sort of top-down organisation. There was a spokesperson under him. There were people who were responsible and reporting to him. But in reality, the people on my team, for instance, I had 25, 50 people, depending on how you counted it, which is in itself a bit weird. But there was no, like I couldn't fire anyone on that team, right? They could be completely useless, and often were. Were all excellent. But I couldn't fire anyone, I couldn't get anyone a pay rise, I couldn't promote them, I couldn't, you know, I had to, the way we had to get stuff done was very much kind of cajoling and saying, you know, this is the right thing to do, pull things through that way. And again, there's another talk this afternoon, tomorrow, Brent Beers talking about this kind of no top-down organisation stuff. So one of the things that gets important in both the processing and also the infrastructure around the processing is the idea of data temperature. So yeah, there are some data that some jobs will always hit. There are some rows in the database that some processes will always have to go through. But spending some time in understanding where you have hot data, where you have cold data, what can you cache, working out that actually I don't need to read this at the kind of finest granularity, I can look at something higher granularity, is a really good way of making your system much more scalable. So we had, for instance, that data transfer tool, it was moving around files, but we aggregated files into blocks. So there'd be 1,000 files in a block, and then we aggregated blocks into data sets, so there'd be 1,000 blocks in a data set. So we could say all of the files in this data set are at that site, so I don't need to track the individual files, I can just say this one's there, and that saves you 6 orders of magnitude in your database. Much simpler thing to kind of grok around, and then when someone wanted to transfer that stuff, it would expand out those things as necessary. And that kind of idea of reducing around the sort of active data as much as possible is a really useful trick. We had this interesting thing where there's no now, which is basically CAP theorem. Who knows CAP theorem? Who doesn't know CAP theorem? Right, so CAP theorem is consistency, availability, and partition tolerance. And the idea is that most people, a few people think you can do it without, but most people say that in a distributed system you have to have partition tolerance. So it has to be, your system has to understand that if someone chops the network, it has to be able to recover from that. And either you have a consistent system where you basically say, well, the network's down, I can't talk to my friend over there, so I'm not going to do anything, I'm going to wait. Or you have an available system where it goes down and goes, oh, I recognize that that's down, I'll still take writes and I'll still serve my data, but you as the sort of consumer of that data has to be aware that it may or may not be the freshest data, right? And we had this kind of in spades in the system because, you have a batch queue that's looking at jobs that may or may not be actually running, that then is reporting to a piece of middleware that's may or may not be talking to the batch system correctly or at the right frequency, which is then talking to another piece of middleware, which is then talking to another piece of middleware. It's turtles all the way down. So in a lot of our cases, consistency was very, very difficult to maintain, and in the rest of them it was basically impossible, so we didn't even try. Some of the stuff around, going back to the data temperature idea, cold data tends to be in a much more consistent state because it's not changing, right? So that's a good thing. You can kind of cache that, throw it somewhere in, whack a varnish or whatever in there. So if you can base decisions on your colder data, it's A, more likely to be correct, and B, it's cheaper to use because it's cold data, so that's good. One of the issues with this sort of lack of consistency across this system is that it makes exposing state out to users very, very difficult, right? So I can't tell you, you can't S-trace your job. I can't tell you which job or which file is getting processed by which thing at any one moment and actually be honest about it. So the solution there is to accept the fact that you're going to lie, right? And lie through your teeth and work out how to sort of turn that lie into something useful. So again, the data transfer system, it could do things like the things that were managing the transfers local to the site could be down for some significant period of time, and then they just come back up and report back and correct history. But if you looked at the kind of plot for that 15 minutes where they were kind of resyncing stuff, it looked like you were transferring petabytes a second, which wasn't true. And again, it goes back into that sort of idea of being very, very asynchronous around your components. Following on from that, the idea of, well, if I can't have a global consistent state, I want to try and keep things as local as possible. So I don't want to expose information about the system out to the wider world unless I absolutely have to. That helps with the sort of partition tolerance stuff. So if I don't have to tell every 30 seconds that I'm doing X to the wider world, then it doesn't matter if the network goes down for 20 minutes. Again, it makes monitoring very, very difficult because you're lying. But we had the sort of thing of, well, actually, we can sort of monitor the whole site as the entity and not worry about a node in the batch system. And we had sysadmins at the sites that would worry about the nodes in the batch system, but the global system didn't really have to care about it. That's quite nice. But that sort of thing is very, very hard for control freak physicists to deal with. They really did want to S-trace their jobs. They wanted to have, sub-second accuracy on where the thing were through the processing, because they were, really chomping at the bit to get the first data out. So yeah, obviously, defining monitoring is difficult. It's again a consequence of keeping that data local. And so the idea is to sort of work out, well, actually, what information do I need to propagate through? People have very high expectations around monitoring because they're used to running in sort of one environment that's not the same as the one that they're moving into. It's also a place where people really, really, really like to bike shed. So it's like, oh, this plot's not quite pretty enough. We should spend some more time on it. But that's kind of, again, social problem, not a technical one. One thing we found, any time a small file kind of got into the system, and they did quite frequently, it would cause significant pain and misery. They're inefficient for storage, they're inefficient for transfer, they're inefficient for processing, and they're also inefficient for cataloging. So you actually, we had these very large kind of data catalogs that would say, this data set is made of these files that were recorded at this time with these conditions. And so if you can track 1 million files, that's much better than if you can track 1 billion, right? And we found that in even the worst case of just using tar to aggregate stuff together, that was better, right? Just kind of squish things together as much as you can. Related to that is this idea of compartmentalizing metadata. You will want to search on your data on something that's not just the timestamp of when it was written into the file system, or not just the alphanumeric of the file name. As I said, we had these large metadata catalogs, and they would store substantial, and for some of the sort of smaller stuff, the metadata would be larger than the actual event data, which is kind of interesting. A file can't exclusively contain its metadata, because then you have to look at every single file to understand where you are. And similarly, you can't kind of track things. Again, it goes back to this idea of kind of reducing stuff down to blocks and data sets. If you can take an attribute that is actually the same for all files in the block and throw it and record it at the block level, you're saving yourself 3 orders of magnitude or whatever. We also found that having kind of multiple metadata catalogs that aggregate together into a sort of a kind of consistent view eventually, was better than having a sort of single monolithic one. It meant that you were sort of isolated to failures and stuff. And again, the sort of metadata you want to record is very, very application specific, and you might find that one analysis has something very specific it wants to record, or something different. And having a system that's able to sort of be flexible around that, and that's where we found things like Couch or Mongo were quite nice, because they were sort of freeform and you could kind of just chuck stuff in. You can do it in Oracle as well, but different. Yeah, the other piece is that we also had some interesting problems where basically the file would land and have this kind of initial processing done, and it would update a local metadata catalog saying, you know, this one's landed and been processed okay, and it's got 1,000 events and da, da, da. But it turns out that sort of MySQL doesn't like having 10,000 people write to it at the same time, and you can, if you're not careful, your metadata catalog becomes the bottleneck. So again, going back to the idea of sort of understanding the access pattern, understanding the data temperature is really, really important. So some more sort of huggy stuff. Recognize, embrace, and communicate failures. So things are going to break. Recognize that, don't pretend that they're not. And be really, really good at communicating them out to your users, right? If a system is going down every 20 minutes, and it's because it's under a high load because user X is doing something crazy, then, you know, if you politely say, "Oi, tosser, stop doing that," then they probably will, because they'll understand that they're actually breaking things for everybody. Being really honest about your failure modes helps build credibility, helps getting this kind of this idea of openness around the system out to folk. It increases support and adoption because people are, you know, they'll understand that it's going to break and people are tolerant of that, but they also understand that when it does break, people are going to be really working really hard on it, but also going to be honest in communicating those problems out. And it's another way that you can kind of turn these kind of disruptive users into advocates, right? Like, if you can say to them, you know, hands on the table, honest, you know, this thing's broken because we deployed some bad code, or someone's doing something silly. These people kind of tend to appreciate that, and it's very useful to increase the adoption of the system. Yeah, so a lot of stuff that I ended up thinking about when I was working at CERN was that basically people are harder than computers. A lot of these kind of big data challenges, problems, are actually more about having an effective organization around the software and around the hardware and stuff. So things like openness and around data and the processes that go on around and on that data, change management, configuration management, really effective communication, are much more important than the actual version of the software that you're running, for instance. And that's because people are very important, right? Key things there are to, you know, be nice to folk that are working at weekends. The cost of a person is where you can actually make savings by enabling them to do more with their time. And again, it's, you know, communication is really important, and building these kind of sustainable teams around the systems are actually the key thing. And that's building up that team is very hard. It takes a lot of time. You have to invest in that, but that's essential for success. And it's because of the wonderful formula that you can see that, right? So some of the consequences of this are basically you want to automate everything if you can. Take people out of the loop where appropriate, because they do make mistakes. You have to learn to love a configuration management system. Doesn't necessarily mean it's a complicated configuration management system. It could be some files tracked in a version control system and a person who knows how to push them out, or you could go down, you know, Puppet, Chef, or whatever. Make sure that everyone in the team knows how to interact with that configuration management system is really important from a development point of view. There's nothing more frustrating as a developer than writing code, getting it approved or whatever, and then not being able to push it live. So if you know that, you know, we do a release once a month or every day or whatever, knowing where you fit into that sort of system is really important. And again, this idea of sort of simple human solutions go a long way here. So you can actually do, just by giving someone, you know, empowering someone appropriately, you can actually solve a lot of very difficult technical problems through kind of just talking to people. It's controversial, but it's true. Again, to the sort of point of making people more effective, you've basically got to build very good abstractions. So users of the grid interacted with maybe 20 or 30 different systems when they submitted their job. But from their point of view, there was a web page they looked at and a command line interface, and that was it. And that was very difficult to do, getting to the point where the system is smart enough to be able to deal with all those kind of weird and wonderful failure modes and non-compliant systems was difficult, but it's the only way that you can actually build adoption around this stuff. And you're seeing that with Pig and Hive in the Hadoop community, where people are saying, well, I know SQL, so I want something that looks a bit like SQL. Give me something that will do SQL-ish stuff. It's not necessarily the right, and again, it's going back to doing the right thing, the simple thing, right? If I can just give you a very simple command line tool that you throw a configuration file at, you're going to use that tool versus going out off and working out how to interact with those 30 systems yourself. Encouraging collaboration is really important, from both sort of resource consumption and actually sort of getting things done quickly. Academics tend to collaborate very internal to the communities that they're in, whereas industrial or enterprise folks seem to be much better at collaborating with sort of open source communities and whatnot, which I've always found kind of weird. As an aside, academics love collaborating with an industrial partner. So if you can sort of think of a reason why you should talk to a physics department, toddle down, take them for a beer, and they get like brownie points from the research council and stuff. And you tend to get free labour, right? Which is a good thing. And again, this kind of idea of using this kind of workflow ladder to sort of encourage collaboration. So by saying, let's do this kind of complex, large-scale processing for everyone at the top, and we'll have some guys that do it for the whole organisation. It's a good way to encourage that collaboration. So same thing here you could do with, we're going to have a team that runs the Hadoop jobs that processes everything for the analysts, and we're going to give them, Excel spreadsheets at the end that they can go and hack around on. That sort of way of kind of using the data, which is the thing that people are interested in, as a way to sort of encourage good behaviour is kind of a neat trick. That's the end of my talk. Quick summary. So the interesting thing there is big data is now a commodity. You can buy off-the-shelf software or download it for free from Apache, or find a services company that will do it for you. You don't need to roll your own, and I can assure you don't want to roll your own. The interesting thing there is that building up these kind of large data processing stuff is more about building up the organisation, or as much about building up the organisation as building up the number of machines that you're managing in your data centre. And that's actually a sort of more difficult problem to solve. And then the other thing is, like, just by being a little bit canny and applying maybe a human solution to a problem, that often ends up being cheaper or better than having a ton of people writing some really gnarly, scary code. And there's also that's also where you can sort of make savings and improvements, because you can say, well, today we're going to have a guy that presses the button every 20 minutes, but in 2 weeks' time we'll have a Python script that does it. So yeah, that's the end of my talk. Any questions? Nope? Awesome. Let's go and get coffee. Thanks, everyone.